Right, let's move on to question 5 then. So question 5 is you've got to know about the development of the atom. This comes up quite a lot. They have given you a fair amount of information here, which is helpful. Stuff really you're expected to know. And you cover this in physics and chemistry, so it's definitely worth making sure you've studied this before too long, certainly before your year 11 mocks. Okay. So, you're told here the plum pudding model didn't have a nucleus. What are some other differences? Now, lots of you referred to the fact there wasn't a nucleus in your answer. You couldn't get a mark for that because it said it in the question. Let's talk about 3 other differences. And these are things, I'm just going to list them because these are things you're familiar with. You covered this in class in physics and chemistry. But you should know that the nuclear model is mostly empty space. You've got a tiny nucleus and lots of empty space around it. Okay, so ideally you would say the nuclear model is mostly empty space. You should be really clear about that if you can. And some of you were not clear about which model you were referring to. Okay, you should know a little bit about that nucleus. You're told there's a nucleus. What do you know about it? You expected to know first of all that the nucleus in the nuclear model is positive. The nucleus is positive. You're expected to know also that the mass is concentrated in the nucleus as well. So that was quite a hard one to get. But the other way of getting the mark, so there's a kind of 4th option, if you like, to get 3 of the 4 options, making it clear the electrons are not in the nucleus, they're separate from the nucleus, they're away from it, something like that. Some of you said about the electrons being in orbits or shells. That was fine, that would have got the mark as well. So it's all to do with the electrons separated from the nucleus, something like that. But many of you got the mark for saying they're in shells. Okay, so then a bit more on that then. So Niels Bohr really developed the idea of the electrons being in shells. And many of you got this actually, which was good. So you have to know that what Bohr did and what Chadwick did and what J.J. Thomson did and what Rutherford did. I'm afraid you have to learn all that stuff. But what Bohr did is he said that electrons are in shells, or electrons orbit the nucleus. It's a little bit like the previous question, which is a bit weird. The electrons in shells for 1 mark. But you had to be clear. I thought this was really hard, the 2nd mark. Some of you got it, so well done. But it's all about the fact that electrons are in different distances and fixed distances. So fixed distances or specific distances as in the mark scheme. I prefer though a kind of more key stage 5 answers that there are different energy levels. And some of you said that, which is pretty impressive. But I'd probably better stick to the GCSE answer. The fixed distances from the nucleus. Right, so then Mendeleev developed a periodic table, sorted them back in those days by atomic weight because they didn't know about atomic number, didn't know about, we didn't call it mass number, we used atomic weight. And some people, well, the question says a student suggested Mendeleev Mendeleev reversed the order of some pairs of elements. I see. So the student suggested that Mendeleev reversed the order the reason he reversed the order of some elements was to put them in order of atomic number. But why can't that be true? And it's simply because atomic number was not known about in those times. If we go back to the previous question, you see protons were discovered in the early 1900s, 1915, 18, something like that kind of time. So in 1869, protons had not been discovered. And quite a lot of you got that mark, worked that out from the information given. But you also have to be clear that atomic number equals number of protons. So atomic number of protons. Okay. And then what was the real reason Mendeleev reversed some of the pairs of elements? If you look at a periodic table and see, for example, tellurium and iodine, you'll see that tellurium is heavier than iodine, and immediately Mendeleev would have thought that tellurium should be to the right of iodine. But the reason he switched them back to as they are now, which is tellurium in group 6 and iodine in group 7, is because he wanted the properties of the elements to match others in their group, and that was the answer. So properties have to match the rest of the group. So all the halogens have very similar properties. Properties match to group, or something like that. Would have got the mark. And let's do question 8 as well before I stop. So, what is the state of bromine at 0 degrees and 100 degrees? Now, the information is given in the question. You could have worked this out. So, there's bromine. Its melting point is at -7. So, anything below -7, then it would be a solid. Just like ice has got a melting point of 0, anything below 0, water is ice. Okay. So, bromine's got a melting point of -7. So, below -7, it's solid. Between its melting point and its boiling point, it must therefore be a liquid. So it's solid down here, liquid in between, and a gas up here. Just like water, it would be, for water it would be 0 for its melting point and 100 for its boiling point. Between 0 and 100 it's a liquid. Right, but for bromine at 0, which is in between -7 and 59, it's a liquid. So it has to be one of these two. And at 100 degrees, which is above its boiling point, it had to be a gas. So there we go, so that's the answer. Quite a lot of people got that wrong, and I think that reflects a bit of lack of patience with that question. People are probably just guessing and not really thinking about the information given to them. What is the trend of boiling points of the halogens? Look, the answer's in the question. The boiling point increases as you go down the group. So you have to say, lots of you refer to the melting point, which is a bit silly really, given it's about boiling point. So boiling point increases down the group. No knowledge required for that at all. You simply have to say what was in the question. So boiling point increases down the group, and you have to explain that. And I'm just checking the marks to give you exactly what you have to get for the 4 marks here. But essentially, it's the idea that the molecules, the bigger the molecule, the higher the boiling point. And you've seen this before with, for example, with crude oils. As you get longer chain hydrocarbons, the boiling point increases. Bigger the molecule equals higher boiling point. So that's the second mark. It's the best way of getting the second mark. There's an alternative as well, but increasing size of molecule as you go down the group. You could also have said the formula mass increases or molecular mass increases, but you haven't studied that yet. We'll do that next term. But anything about the size of the molecule getting bigger. And the reason that the size of the molecule getting bigger is important, just like I said in that first question I did, if you've got a big molecule, you've got more intermolecular forces, more contact points between molecules. So if you've got a long chain hydrocarbon, for example, versus a short chain, the long chain hydrocarbon has stronger forces of attraction, stronger intermolecular forces than the smaller molecule. That's the same with the halogens. If you've got little tiny fluorine, F2, versus very big bromine molecules are very big, and so the intermolecular forces between bromine and another bromine molecule are stronger. So that's what you have to say. So increasing intermolecular forces, and you have to say then, so more energy needed to overcome them. And this 4th mark is very common in the GCSE. So more energy needed to overcome those intermolecular forces. This question's quite hard, I think, quite hard to get the mark for this one, so well done if you did. Boiling point of a single bromine molecule. Well, some of you got the idea, I think, that you can't boil a single molecule because you've got to overcome intermolecular forces, which means you need at least 2 of them. But the way that you have to get the mark is by saying something like boiling is a bulk property. In other words, when you've got lots of them. I don't suppose many people used that terminology, but there was an alternative, which is you have to make a comment about the fact that boiling point links to intermolecular forces, and so more than one molecule is needed. Try to mark this fairly generously. really you should be saying, look at this experiment here. You've got iron, there's the iron, reacting with halogen. Halogen being passed through in a gas, it could be something like bromine, being passed through a tube, a glass tube, which is being heated up with iron inside it, like iron wool or something. It's done in a fume hood. Why? Well, because halogens are toxic to breathe in. And really, that's what the mark should be for. The halogen is toxic. Sorry about the spelling there. Halogen is toxic, or the gas is toxic, or the gas is poisonous, or the gas is harmful, or the halogen is harmful. If you said something about to avoid having to breathe in the halogen, then you get the mark. But it said ignore words like lethal or deadly, because it's not necessarily going to kill you unless you breathe enough of it in, but you have to say that it's toxic. Now, you should know the halogens are toxic. You know, for example, that chlorine was used as a weapon, chlorine gas back in the First World War. So you know link this idea with your history that chlorine is a toxic gas. Okay, so what have we got next? Explain why the reactivity decreases down the group. All right, so I'm going to start with just drawing a picture of a fluorine atom to remind you what the group 7 atoms sort of look like. Why does the reactivity decrease? Well, you have to understand that they react by gaining an electron. So when fluorine reacts, it gains an electron. The electron goes into that outer shell. So you don't get a mark for understanding that, but it's helpful to get your head around that. Now, if you compare that to chlorine, which has got an extra shell because it's one row further down the periodic table, that chlorine reacts in the same way in that it gains an electron. The electron goes into that outer shell, but that electron is going into a shell that's further away from the nucleus. Right, and that's the first mark, so I'm not going to write it down. But the electron is going into a shell that's further away from the nucleus, and that means the attraction between the nucleus, which is positively charged, and that outer shell, or where that electron will end up, is greater. So that's the second mark. There's less attraction because it's further away, and so simply then that the electron is gained less easily. Just go through that again. First mark for making it clear that chlorine has got an extra shell, and therefore the electron is less attracted to the nucleus because it's further away, and so the electron is gained less easily. So understanding how they react is a nice thing to be able to do. I'm going to stop there and do the other question 8, the question 8 for paper 2 on a separate video.